Hello, hi dear friends, welcome to yet another session of Mission Bank. Yes, from this session onwards we are starting our preparations for entrance examinations and we are starting our preparation with physics paper. As I told in the previous session, we have to cover almost 28 chapters in physics paper, and in this session we are going to discuss some of the very basic concepts discussed in the very first chapter, that is units and measurements. In this chapter they have discussed some small things which one should know, and we are going to discuss those small things. Yes, shall we move on to our session? Yes, let's start. Units and measurements. Yes, before going deep into this chapter, first we will see what is the need of learning units and measurements in physics paper, because usually we used to learn units and measurements and related topics in maths paper, isn't it? Yes, in school days we were learning units and measurements and related concepts in maths paper. Say for example, how do we measure the length of a line, or what is the length of the line, what are the different units of length, or how do we measure the volume of liquids, what is the unit of the volume of liquid, what are the different units of weight, or else convert these values from kilogram to gram, etc. like concepts we were learning in, or we used to learn in maths paper. Then now why we are learning it in physics paper, and also that too in the very first chapter. This units and measurements is the very first chapter in the physics paper. So yes, first let's understand what is the need of learning units and measurements in physics. Yes, what is physics? Physics is the study of universe, or it is better to say physics is the study of the nature of the behavior of universe, isn't it? Yes. What is universe made up of? Universe is made up of matter and energy. Yes. What is matter? Matter is nothing but anything that occupies space. Anything that occupies space is known as matter. I am a matter, you are a matter, or this marker is a matter, or we can say this board is a matter, or water is a matter, or oxygen is a matter, or carbon dioxide is a matter. Anything that occupies space, no matter which state it is. As we all know, we have three states, isn't it? Solid state, liquid state, and gaseous state. Say for example, yes, ice is in solid state, oil, milk or water etc. are in liquid state, oxygen, carbon dioxide or nitrogen etc. are in gaseous state. So no matter which state it is, if it needs some space to occupy, we can call it as a matter. And these matters may have so many properties, such as physical properties or chemical properties, and some may have some biological properties. Yes. And the physical properties of the matter, among the physical properties of the matter, some can be measured and some others cannot be measured. Yes. What does it mean? It means some of the physical properties, say for example, physical properties like length, mass, volume, etc. can be measured. Say for example, yes, the length of this marker can be measured, or the mass of this marker can be measured, or the density of this marker can be measured, isn't it? Yes. But some other physical properties like color, can we measure the physical property color? Can we measure the physical property color of this marker? No, it is not possible to measure the physical property color. Yes. So in short, some of the physical properties of a matter can be measured and some others cannot be measured. So all those physical properties of a matter which can be measured are known as physical quantities. Measured are known as physical quantities. Physical quantity is singular and physical quantity is plural. Yes. And to understand the nature of the behavior of a matter, or to study the nature of the behavior of a matter, we need to measure these physical quantities. Yes. Once we understand the nature of the behavior of each and every matter in the universe, yes, It's enough to understand, the nature of the behavior of the whole universe, isn't it? Yes. So to understand the nature of the behavior of these matters, we need to measure the physical quantities of these matters. Yes, that is the importance of learning measurements in physics. Is it clear? Yes. Now let's see what is the need of learning units in physics. Suppose without showing my marker, I am telling you I have a marker and its length is 10. Simply 10. I am telling you its length is 10. Yes. Can you guess the actual length of the marker? Do you get a clear-cut idea about the length of the marker? No, nobody gets a clear-cut idea about the length or any other physical quantity if I simply say 10 or any other numerical value, isn't it? Yes. Suppose now I am showing you this cap and I am telling you I have a marker and the length of this marker is 5 times the length of this cap. Yes. Now you can guess the actual length of the marker, or now you will get a clear-cut idea about the length of the marker. Again, I am showing you an eraser of different length and I am telling you I have a marker and the length of the marker is 10 times the length of the eraser. Yes. Now also you will get a clear-cut idea about the marker, isn't it? Yes. So in short, in order to get a clear-cut idea about any physical quantity, we need to compare the measured value. Of the physical quantity with a standard value of same quantity. Means I have to compare the measured value of mass, or I have to compare the measured value of mass with the standard value of the physical quantity mass itself. Or I have to compare the measured value of length with the standard value of the length, etc. Yes. And these standards with which we compare the measured value is known as units. It's units. Yes. Again, we chose two different standards here, isn't it? In the example I told you, I chose two standards. The first one was a cap and the second one was an eraser, isn't it? Again, suppose I am telling you I have a pencil of a different length and the length of the marker is exactly the same as the length of the pencil. Yes. Now also you will get a clear-cut idea about about the length of the marker, isn't it? Yes. So we could choose different standards. To compare the physical quantity. Just like that, a single physical quantity can be measured in different units. A single physical quantity can have so many units. Say for example, for length we have centimeter, we have millimeter, we have meter, we have kilometer, etc. Isn't it? Yes. Again, the standards which we chose in the example, like the cap and the eraser, had a fixed length, isn't it? Yes. We are comparing the measured value of the matter with a standard length, isn't it? Yes. Just like those standards, just like the cap and eraser, the units also have the units of a physical quantity also have a predefined fixed value. The units of a physical quantity also have a predefined fixed value. Yes. The length of the cap, the fixed length of the cap was not equal to the length of the eraser, or it was not equal to the length of the pencil, isn't it? Yes. Similarly, the fixed value of centimeter is not equal to the fixed value of millimeter. It is not equal to the fixed value of meter. It is not equal to the fixed value of kilometer. Yes, it can be either smaller or it can be larger. It can be either smaller or it can be larger. Yes. So, if I am telling you the length of my marker is 10 centimeter, what does it mean? 10 into fixed value of centimeter. Yes, 10 into fixed value of centimeter. Suppose I am telling you the mass of my marker is 10 kilogram. Yes, what does it mean? It means 10 into fixed value of kilogram. 10 into fixed value of kilogram. Is it clear? Yes. Now I have two markers A and B, and the length of my marker A is 1000 centimeter and the length of my marker B is 50 meter. Length of my marker A is 1000 centimeter and the length of the marker B is 50 meter. Yes, and you are asked to find the marker having greater length. Which marker has greater length? You are asked to find the length of which marker, or which marker has greater length. Yes. Is it possible to find? Yes, it is possible to find. It is possible to compare. Similar physical quantities of two different matters. Similar physical quantities of any number of matters. It is possible to compare similar physical quantities. It is possible to compare similar physical quantities of any number of matters. Yes, and here we are asked to compare. The length of two matters A and B. Yes, but since it is hard to compare the values if it is measured in two different units. It is hard to compare the values or compare the physical quantity if it is measured in two different units. Yes, there comes, in order to compare similar physical quantities, there comes the need of conversion of units. Yes, that is, either we have to convert the length of both the markers. Either we have to find the length of both the markers in meter or else in centimeter. So how do we convert the values in one unit to another unit? Yes, first we'll derive a relationship. Between, or relationship connecting both the units. Here in this example we have two units, centimeter and meter. First we'll derive a relationship connecting both the units. Yes, how do we derive a relationship connecting these two units? We know all these units have a predefined fixed values, isn't it? Yes, by equating those two fixed values, yes, we can derive the relationship between these two units. Yes, by equating the fixed values of centimeter and meter, yes, we have derived a relation as 100 centimeter is equal to 1 meter, or 1 centimeter is equal to 0.01 meter. Yes, now either we can substitute 100 centimeter, either we can substitute 100 centimeter for meter. Either we can substitute meter by 100 centimeter. Yes. So we'll get both the lengths in centimeters, or else we can substitute 0.01 meter for this centimeter. So we'll get both the lengths. Then we'll get both the lengths in meter. Yes, let's see. I am substituting 100 centimeter in the place of meter. Okay. So a length of A is 1000 centimeter and length of B is 50 into 100 centimeter. So the length of B is 5000 centimeter. Yes, whose length is greater? Yes, marker B has greater length. Again I am substituting Here the length of marker B is 50 meter and I am substituting centimeter. I am substituting centimeter by 0.01 meter. Yes, 1000 into 0.01 meter and my length becomes 10 meter. So length of marker A is 10 meter and length of marker B is 50 meter. Yes, who has greater length? Marker B has greater length, and we got the same answer. We got the same answer in both the cases. Yes. So that is the importance of learning units and conversion of units in physics. Yes. Is it clear? Is it clear why we are learning units and measurements in physics? Yes. Now let's see physical quantities in deep. Yes. So what are physical quantities? Physical quantities are nothing but the the physical properties of a matter, which can be measured. Yes. How do we express a physical quantity? For expressing a physical quantity, or we express a physical quantity by a numeric value, say for example 20, by the measured value along with its unit, by a measured value and a unit, we express a physical quantity by a measured value with its unit. Yes. And the measured value, the numerical value along with its unit is known as magnitude. The numerical value along with its unit is known as magnitude of a physical quantity. The term magnitude is very, very important in physics because we hear this word or we hear this term throughout the physics paper. We hear this word in all the chapters. Yes. So what is magnitude? Magnitude is the numerical value along with the unit, or the measured value along with its unit of a physical quantity is known as the magnitude of physical quantity. Yes. Yes. The physical quantities can be classified into two, as fundamental quantities or base quantities. Fundamental quantities are otherwise known as base quantities. Again, derived quantities. So physical quantities can be classified into two, as physical quantities are classified into two, as fundamental quantities and derived quantities. Yes. What are fundamental quantities? Those physical quantities which do not depend on any other physical quantity for its measurement. Say for example, I am measuring the length of this marker. Yes. Does the physical quantity length depend on any other physical quantity for its measurement? No, it doesn't depend. Again, I am measuring the mass of this marker. Does the quantity marker depends on any other physical quantity for its measurement? No, it depends on it. It does not depend on any other physical quantity. Say for example, again I am measuring the density of this marker. Does the quantity density depend on any other physical quantity for its measurement? Yes, it depends, isn't it? It depends on two other physical quantities, that are mass and volume. Again the volume depend on some other physical quantities like length, base area, etc., isn't it? Yes. So here the length and mass, here the physical quantities length and mass do not depend on any other physical quantity, for its measurement. Such quantities are known as fundamental quantities or base quantities. So then what are derived quantities? Yes, derived, as the name implies, derived quantities are derived from some other quantities, just like density. Yes, they are derived from some other quantities. Yes. So examples of fundamental quantities: length, mass, time, etc. Here volume, speed, or we can say density, etc. Yes. The units of fundamental quantities or base quantities are known as fundamental units or base units. Fundamental units or base units. The units of fundamental quantities or base quantities are known as fundamental units or base units, and the units of derived quantities are known as derived units. The units of derived quantities are known as, and we can find the units of derived quantities. We can find the units of derived quantities from the fundamental quantities, or from the units of fundamental quantities on which it depends, on which the derived quantity depends on. Is it clear? Yes, we'll discuss it later on. Yes, now just for the time being, you just understand, yes, derived units can be derived from fundamental units, or derived units can be derived from the units of the physical quantities. Derived units can be derived from the units of the physical quantities on which the derived quantity, on which the respective derived quantity depends on. Yes. Say for example, density depends on two other physical quantity, that is volume and mass. So we know the volume of the unit of volume is meter and the unit of mass is kilogram. So we can find the unit of density. We can find the unit of density from these two units. We can find the unit of density, or the unit of density will be a combination of the units of volume and mass, or otherwise we can say the units of derived quantities. The units of derived quantities will be the combination. It can be either in product form or it can be either in division form. Whatever it may be, the units of a derived quantity will be the combination of the units of the physical quantity from which they are derived. Is it clear? Yes. And the collection of these fundamental units and derived units, or the set of fundamental units and derived units are known as system of units. The set of fundamental units and derived units are known as system of units. Yes, is it clear? Fundamental quantities, base quantities, fundamental units, derived units, and system of units. Yes. Now let's see a few more about physical quantities, and then we'll move on to the next topic, system of units. Yes. Yes. We need to describe the physical quantities. And how do we describe a physical quantity? Yes, let's understand it through an example. Suppose there are two places A and B. Yes, and obviously there will be a distance between these two places, isn't it? There will be a distance between any two places, isn't it? Yes. So there is a distance between A and B, between the two places A and B. Yes. This distance is a physical quantity. I have to describe the physical quantity distance. Yes. How do I describe the physical quantity distance? Yes, I can describe the physical quantity distance by its magnitude, isn't it? What is magnitude? The measured value or the numerical value along with the unit is known as the magnitude of a physical quantity. Yes. So I can describe the physical quantity distance by its magnitude, isn't it? Yes. Should I consider the direction of this physical quantity, direction in which this physical quantity takes place while describing the physical quantity distance? Should I consider? No. That is, either the distance is from A to B or the distance is from B to A. Should I consider it? No, there is no need of considering it. There is no need of considering the direction while describing the physical quantity distance. Suppose I am calculating or I am finding the volume of a sphere. Say for example, I am finding the volume of a sphere, or I am finding the density of a sphere. Yes, I have to measure these physical quantities like volume, density, etc. So I can describe them by its magnitude. Say for example, the volume of the sphere is 29 meter cube. The volume of the sphere is 29 meter cube. Or the density of the sphere is 2.6 kilogram per meter cube. The density of the sphere is 2.6 kilogram per meter cube. Likewise, I can describe these physical quantities by its magnitude. So, to describe these physical quantities, should I consider the direction? Should I consider the direction in which the physical quantity volume is taking place, or should I consider the direction? Should I consider the direction in which the physical quantity density is taking place? No, there is no need of considering direction. For some physical quantities, for their description or for describing them, yes, we only need their magnitude. Is it clear? Yes. Suppose again, say for example, there are two places A and B. Here we are considering another physical quantity, displacement. Here we are considering another physical quantity, displacement. What is displacement? What is the meaning of the word displacement? Displacement means change in position. Displacement means change in position. Okay. A shift in the position. So I am telling Manu displaced, yes. Let the distance between these two places A and B, yes. I am telling you Manu, a boy named Manu displaced. I have to describe the physical quantity. Displacement. Yes, I can describe the physical quantity by its displacement by its magnitude, isn't it? So Manu displaced by 100 kilometer. Yes, but is the description of displacement complete if I simply describe it by its magnitude? No, the description is not complete. In this case, I have to consider the direction in which the physical quantity displacement takes place. That is either from A to B or from B to A. That is Manu displaced 100 kilometer. Manu displaced 100 kilometer from A to B, or Manu displaced 100 kilometer from B to A. Yes. So for describing some physical quantities, we have to consider both its direction and magnitude. That is, some physical quantities have both magnitude and direction. Again, let's see one more example. Yes, force. Yes, there are two objects. There are two objects. Yes, let this be a road. There are two objects A and B like this. There are two objects A and B like this. Yes, and a force is acting. A force is acting between A and B. Let it be 10 Newton. 10 Newton. Yes. So here I have to describe the physical quantity force. Yes, I can describe the physical quantity by its magnitude, that is 10 Newton. The force here is, or the force applied here is 10 Newton. But the description is not yet completed. That means I have to mention who is applying force, the application of the direction of the application of the force should also be considered or should also be mentioned. So force for some quantities or some physical quantities like displacement, force, etc. Yes, we have to describe. For describing these physical quantities, we have to consider both its direction and magnitude. That is, some quantities have both direction and magnitude. Suppose again, let's see another physical quantity, stress. Yes, for some quantities like stress, strain, or thermodynamic conductivity, etc., those quantities take place in more than one direction. Here the physical quantity displacement or force acts acts in a single direction, acts in a single direction. But some quantities like stress or strain or thermodynamic conductivity, etc., acts in more than one direction. So for describing these quantities, yes, we need to consider its magnitude, and we have to consider more than one direction, isn't it? Yes. So there are three types of quantities which have magnitude only, quantities which have both magnitude and one direction, and quantities which have magnitude and more than one direction. Yes. So for describing each of these physical quantities, we have three mathematical objects, that is scalar, vector and tensor. So for describing physical quantities who has only magnitude, we use scalar. And we use the mathematical object scalar, and such quantities are known as scalar quantities. So what are scalar quantities? Scalar quantities are those quantities which have only magnitude, And for describing quantities who have both direction and magnitude, we use the mathematical object vector. To describe them. And such quantities are known as vector quantities. Yes, so what are vector quantities? Vector quantities are quantities which have both direction and magnitude. And for describing physical quantities who have more than one direction, we can use the mathematical object tensor. Yes. And in your syllabus you have to learn only two mathematical objects, that is scalar and vector. Yes, they excluded the third mathematical object tensor. They have only included two of the three mathematical objects, that is scalar and vector. But just for your knowledge, we'll see just what is what of tensors. Yes, and we can classify these tensors. Into various types based on the number of directions in which those physical quantities or in which those tensors are taking place, that is zero rank tensor, first rank tensor, second rank tensor, and it goes on like this. Zero rank tensor, first rank tensor, second rank tensor, third rank tensor, likewise it goes on. What is the rank of a tensor? Rank of a tensor is nothing but the number of directions in which the physical quantity takes place, So what is zero rank tensor? Zero rank tensor is a physical quantity, which has no direction. That means zero rank tensor is otherwise known as scalar quantities, or scalar quantities are otherwise known as zero rank tensor, because those tensors or those physical quantities only have magnitude, they don't have any direction. And what is first rank tensor? First rank tensors are those physical quantities which have only which have magnitude and only one direction, So such quantities are otherwise known as vector quantities. So what are first rank quantities or vector quantities? They are physical quantities which have magnitude and only one direction. Again, what is second rank tensor? Second rank tensors are those physical quantities which have two directions. Say for example, stress, strain, thermodynamic conductivity or electric susceptibility, etc. like quantities takes place or acts in two directions. What is third rank tensor? Third rank tensors are physical quantities which have 3 directions. Say for example, we can say piezoelectricity or piezoelectricity. Yes. Again, 4th rank tensor. What is 4th rank tensor? They have 4 directions, or they they acts in 4 directions. Say for example, stiffness. What is 100th rank tensor? Those physical quantities takes place in 100 directions, acts in 100 directions, and it goes on like this. Yes. Now, so we used to describe these quantities using numbers. We used to describe these physical quantities using numbers. So, in order to find the count of the numbers required, to describe a physical quantity, we have an equation 3 power n. We have an equation 3 power n, and this n is nothing but the rank of a tensor. So, for finding the so how many numbers are required to describe a scalar quantity? 3 power 0 is equal to 1. Only one number is enough to describe a scalar quantity. And again, how many numbers are required to describe a vector quantity? We need 3 numbers. To describe a vector quantity or first rank tensor. How many numbers are required to describe a second rank tensor? We need 9 numbers. Yes. It's not product. Yes, it's exponential form. It is not 3 into n. It is 3 power n. 3 to the power n. So, it is in exponential form. Is it clear? So, how many numbers are required to describe a 100th rank tensor? 3 power 100. Yes. Is it clear? Yes. So, how do we represent a scalar quantity, or how do we represent a vector quantity? Yes. For representing a scalar quantity, or the symbol of a scalar quantity is nothing but simply the symbol of the physical quantity. Say for example, distance. Let the symbol of the physical quantity distance be d. Yes. If I simply write d, it means this physical quantity is a scalar quantity. Suppose I have to represent a vector quantity. Say for example, force is a vector quantity, and the symbol of force, let it be F. So, in order to represent a vector quantity, yes, I have to write an arrow. About the symbol of the vector quantity. Is it clear? Scalar quantities and vector quantities. And also, we have just discussed what about scalar quantities and vector quantities, because yes, we'll see these scalar quantities and vector quantities. We'll see these scalar quantities and vector quantities in detail in some other chapter. Yes, we have to study dot product or cross product or vector law, triangular law of vector addition, or else yes, all the operations or identities related to all the operations and identities of these scalar quantities and vector quantities will be discussed in some other chapter. Yes, now just for the time being, yes, you just need to understand these basic things. Is it clear? Yes. Now we'll move on to the next topic, system of units. System of units. Yes. In earlier times, people around the world were not globally connected, isn't it? Yes, we can say the countries were like separate entities. Yes, the scientists of these different countries were in a need of choosing a unit as standard for the physical quantities. The scientists were in a need of choosing a unit as a standard for all the physical quantities. Yes, so what they did is, since they were not globally connected, scientists of different countries chose different units as standards. Yes. So there were there were based on the units they chose as standards. Based on the unit they chose as standard. There were 3 system of units, CGS, MKS and FPS. CGS, MKS and FPS. Yes. Also, in those days they had only 3 fundamental quantities. They had only 3 fundamental quantities, and these 3 fundamental quantities were enough then to derive all the physical quantities which they were dealing with then. Yes. And those 3 fundamental quantities were length, mass and time. Yes, length, mass and time. They could derive they could derive all the quantities, all the physical quantities which they were dealing with then from these 3 fundamental quantities. Yes. And the unit of length in CGS system was centimeter. The unit of mass was gram, and the unit of time is second. Again, the unit of length is meter in MKS system. In mass it is kilogram. For mass it is kilogram, and for time again same unit, second. And in FPS system, yes, the unit of length is foot in FPS, and the unit of mass is pound, and the unit of time is one and the same, second. Yes. The first letter of each unit is used for the naming of each system. Isn't it? Yes, the very first letter of each unit is used in the naming of these 3 systems. Yes. So is it clear? In earlier days there were 3 system of units based on the units which they choose as standard. Yes. But now the people around the world are globally connected. So now the scientists of all the countries are following a single and same system of unit, and it is international system of unit. International system of unit. In short, it is known as SI system. Yes. Now the science and technology has grown, isn't it? Yes. And we made so many discoveries. Yes, we made so many inventions. And so now these 3 quantities are not enough to derive all the physical quantities which we are dealing with now. So what scientists did is they added some more quantities. In the list of fundamental quantities. So now so far we have 7 fundamental quantities. In SI system we have 7 fundamental quantities and 2 more angular quantities, and these quantities are enough to derive all the physical quantities which we are dealing with now. So let's see what are those 7 fundamental quantities. Length, mass, time. Yes, these 3 quantities are there, to which we added 4 more, that is luminous intensity, amount of substance. Yes, AMT is amount of substance. Okay, amount of substance. Then electric current, temperature. Yes. The unit chosen as a standard for the physical quantities, for each physical quantities are known as SI units. The units chosen as standards for the physical quantities in SI system is known as SI unit. Yes. So the SI unit of length is meter. The SI unit of mass is kilogram. The SI unit of time is second. The SI unit of luminous intensity is candela. The SI unit of the amount of substance is mole. The SI unit of current, electric current, is ampere. The SI unit of temperature, the SI unit of temperature is Kelvin. Yes, even though we commonly use degree Celsius or we commonly use Fahrenheit for temperature, isn't it? Yes, for measuring fever and all. Yes, we use the unit degree Celsius or degree Fahrenheit. But the SI unit of temperature is not degree Celsius or Fahrenheit, but it is Kelvin. Okay. And the symbol of the unit meter is M. The symbol of the unit kilogram is kg. Second is S. Candela is CD. Mole is MOL. Ampere is A. And Kelvin is K. Is it clear? So there are 7 fundamental quantities in SI system, and these are the SI units of each of these fundamental quantities. Is it clear? So suppose in examination they ask you to find maybe the density of a sphere in SI unit, yes, then you have to use the units, the SI units of those physical quantities from which the physical quantity density is derived. We know the physical quantity density is derived from two quantities, mass and volume. Yes, so to find the SI unit of density, we should use the SI unit of mass and we should use the SI unit of volume. Yes, if they have not mentioned any particular system, yes, you can choose any unit as your own. Yes, is it clear? Yes, now let's see the two angular quantities in SI system. Yes. So now let's see the two angular quantities in SI system, that is plane angle and solid angle. Yes. And plane angle is something which we are, isn't it? Plane angle is something we are familiar to. Yes. What is plane angle? Plane angle is nothing but the space formed between two lines when they meet at a point or when they intersect at a point. That is, suppose there are two lines like this. And yes, those two lines intersect at this point, and a space is formed, and the space thus formed is known as angle. The space that thus formed is known as angle. We can use any symbol to denote an angle, that is theta or ohm or omega, anything we can use it, but generally we use theta. Yes. The SI unit of an angle is radian. Yes, SI in maths we are used to the unit degree, isn't it? For measuring angle we usually use the unit degree, isn't it? 45 degree, 100 degree or 360 degree, likewise we use the unit degree. But actually the SI unit of plane angle is a radian and the symbol is rad. Yes, and we have derived a relationship connecting the two units degree and rad, that is 1 degree is equal to pi by 180 rad. 1 degree is equal to pi by 180 rad, where pi is equal to 3.14 or 22 by 7. You can use any of these values, any one value of these two values. Yes. So suppose in the examination it is given like, suppose you are given the angular measurement as 45 degree. How do we find the value in rad? 45 into pi by 180. So we will get pi by 4 rad. So 45 degree is equal to pi by 4 rad. Is it clear? Yes. Again. So now let's derive an equation for the angular value theta. So I am drawing a circle whose center is, I am drawing a circle whose center is the point of intersection of these two lines. I am drawing a circle whose center is the point of intersection of these two lines, like this. Drawing a circle like this. Yes. These two lines intersect at 2 points on the circle, isn't it? These two lines intersect at 2 points on the circle. Yes. An enclosed area is formed then, isn't it? Yes, an enclosed area is formed, and this shaded part is known as sector of a circle. This shaded part is known as sector of a circle. Again, when these two lines intersect at any 2 points on the circle, yes, in between these two points there is a circular part. And this circular part is known as arc. The circular part within the 2 points, between the 2 points, is known as arc, and the length of the arc is known as arc length. Length of the arc is known as arc length. Again, the line connecting the center of a circle and any point on the circle is known as radius, isn't it? Yes. The line connecting or the line joining the center of the circle and any point on the circle is known as radius. And we have an equation connecting this angular measurement, arc length and radius, and it is theta is equal to arc length divided by radius. Theta is equal to arc length divided by radius. Is it clear? Yes. The maximum angle or the total angle at the center of the circle, the total angle that is formed at the center of the circle is 360 degree or 2 pi rad. The maximum angle that could be formed at the center of the circle is 360 degree or 2 pi rad. Suppose I am telling you the angular measurement at the center of a circle is 540 degree. Yes, is it possible? No. It's only possible, the angular measurement at the center of the circle is only possible up to 360 degree or 2 pi rad. 0 to 360 or 360 degree or 0 to 2 pi rad. Yes. Is it clear? Plane angle? Yes. Now let's see solid angle. What is solid angle? Yes. Solid angle is a two-dimensional angle. Solid angle is a two-dimensional angle formed in a three-dimensional space. Means what? Yes. Since I couldn't draw sphere in this 2D surface, I'll show you what is solid angle in a cube. So assume this as a hollow cube. We know hollow cube is a 3D space, isn't it? Hollow cube is a 3D space. Yes. And I am taking any 2 points on any of the two surfaces, of a cube. Yes. And I am drawing two lines. I am drawing lines from these 2 points, and these two lines intersected at a point inside or within the hollow cube, isn't it? They both met at a point, or intersected at a point within the hollow cube, isn't it? Yes. And the angle then formed is known as solid angle. Yes, the angle is formed by two lines. The angle is formed when just two lines got intersect, isn't it? The angle is formed when just two lines got intersect. Yes, got intersected. So the angle is a two-dimensional angle, but the angle is formed in a three-dimensional space, isn't it? The angle is formed in a three-dimensional space. So the two-dimensional angle formed in a three-dimensional space is known as solid angle. Three-dimensional space, say for example cube or cuboid, cone, or we can say cylinder, or else we can say sphere, hemisphere, etc. Yes. When an angle is formed in these 3D spaces, such angles can be called as solid angle. Is it clear? Yes. And also the SI unit of a solid angle is a steradian, that is SR. The SI unit of the solid angle is a steradian, and that is SR. Just like degree and rad, we have a relationship connecting steradian and square degree. 1 square degree is equal to pi by 180 the whole square steradian. 1 square degree is equal to pi by 180 the whole square steradian. Is it clear? Here also the value of pi is nothing but 3.14 or 22 by 7, and you can use any of these two values. Yes. Now let's derive an equation. For solid angle. For deriving an equation for plane angle, yes, we choose a circle. So for deriving an equation for solid angle, here we are going to choose, or here we are choosing a sphere. So this is solid angle, this is not circle, this is sphere. Okay, this is sphere. So the center of the sphere is the point of intersection of these two lines. The center of the sphere is the point of intersection of these two lines, and this is not circle, this is sphere. Imagine a sphere. Okay. The line joining the center of a sphere, and any point on the surface of the sphere is known as radius. So these two are radius. Again, the angle formed is theta, and it is solid angle. Is it clear? Yes. So here in plane angle, when we considered a circle, yes, we got an arc and arc length. But here, instead of an arc, we get an area or a portion of the surface. We get, instead of an arc, here in the case of solid angle, since this angle is formed in a three-dimensional space, we get a portion of the surface, isn't it? We get a portion of the surface. Yes, and the area of this portion is known as intercepted area. The area of the shaded portion is known as intercepted area. So what is intercepted area? Yes, we are looking at the surface of a sphere from this point of intersection, that is center of the sphere. From the point of intersection, we are looking at the surface. Yes, some portion of the surface, some portion of the sphere, or some portion of the surface of the sphere will only be visible, isn't it? Yes. The whole sphere will not be visible when we are viewing the surface in this direction. When we are viewing the surface along the lines, when we are viewing the surface in the direction of these two lines, yes, only some portion of the sphere is visible. Only some portion of the sphere is visible. And the area of this visible portion is known as intercepted area. Is it clear? Yes. So there is an equation connecting all these. Theta, that is solid angle, is equal to intercepted area divided by radius square. Solid angle is theta is equal to intercepted area divided by radius square. So what is intercepted area? We are viewing at the surface from the point of intersection, along the direction of these two lines, So only some particular portion of the surface will be then visible. And the area of that visible part of the surface, visible portion of the surface, is known as intercepted area. Is it clear? Yes. So the relationship connecting solid angle, intercepted area, and radius is theta is equal to intercepted area divided by radius square. Is it clear? Yes. Just like plane angle, here also the total angle or the maximum angle that could be formed around the center of a sphere is 4 pi steradian. 4 pi steradian. The total angle that could be formed around the center of a sphere is 4 pi steradian. Yes. So that's all about plane angle and solid angle. Is it clear? I do believe everything is clear to you, isn't it? Yes, because I have discussed everything in detail, isn't it? Yes. Still, if you have any doubts, you please feel free to ask in the comment section. If I could explain it there, then I will explain it there, or otherwise I will explain it in any of the upcoming sessions. Yes. So that's all for today's session. Yes, so we'll see. Just a quick recap. Let's see a quick recap of the topics which we discussed today. First, we discussed what is the need of learning units and measurements in physics. Then we discussed what is physical quantities, two different types of physical quantities and their units. Then we discussed the system of units, isn't it? We discussed the three system of units which were there in earlier times and the current system of unit which we are following. The 7 fundamental quantities and the 2 angular quantities in SI system. And we discussed what is scalar quantities and what are vector quantities and also what are tensors. Yes, is it clear? Understood? Yes. So let's wind up today's session. Still we have some more basic concepts. To discuss, and let's discuss those concepts, in the next session. So see you again in the next session. Till then, bye bye.